Okay, so this is the method 3, that is calorimeter. I would write here method 3. So calorimetry is a technique used to measure changes in enthalpy, that was delta H, of chemical reactions. So we are talking about an experimental technique. Okay, so a calorimeter is made up of a polystyrene cup, then we have a vacuum flask, and we have another thing, that is either you can use a vacuum flask, or you can use a metal can. So we are setting up the calorimeter. Okay, let me show you the diagram. This is basically a simple calorimeter. Okay, we have a polystyrene cup, then we have added the reaction mixture in it. Okay, then we have a plastic lid on top, and thermometer is inserted inside the cup. Okay, and it is, the bulb is within the reaction mixture. This is a basic setup of the calorimeter. Okay, now how the calorimeter measures the enthalpy. Okay, for that we will be using so the energy needed. First we will be calculating how much energy we need, okay, to raise the temperature by 1 degree. So the energy needed to increase the temperature of 1 gram of substance by 1 degree Celsius is called specific heat capacity. Okay, so what are we calculating? Specific heat capacity. So first we need to know what is the specific heat capacity. So it is the energy, okay, how much heat we need to raise the temperature of 1 gram of any 1 gram of a substance by 1 degree Celsius. So we will need that. Okay, it is a fixed value, you can say. Every substance has a different value of specific heat capacity. Like every substance has a different value for density. Okay, so it is same. Specific heat capacity is same. For example, the specific heat capacity for water is 4.81. Okay, it is a general, I think you should remember it. It was, yeah, sorry, I forgot, yeah, 4.18. So, specific 18 joule per gram per degree centigrade. Okay, or per degree Celsius, you can say. Then, moving on. So, how we can calculate the energy transfer? Okay, so for that we have the formula, that is, first we will be using this formula, that is Q is equal to M, then you have C, then you have delta T. Okay, first we will be using this formula. Q is what here? Q is change in heat. Okay, the amount of heat that is being transferred. Either it is transferred to the system or from out of the system. M is what? M is the mass of substance. Okay, the mass, you can say here the mass of water. Okay, so C is what? C is specific heat capacity, and the delta T is what? Change in temperature. Okay, so let's now do a question for it, then we will get a more idea of how the things are going here. In a calorimetric experiment, 2.5 gram of methane is burned in excess oxygen. 30% of the energy is released during combustion is absorbed. Okay, 30% of the energy that was released during combustion that is absorbed by 500 gram of water the temperature of which rises from this to this, and specific heat capacity of water is 4.18. What is the total energy released per gram of methane burned? Okay, so first we need to find the energy. Okay, so what are we going to do is first we will be calculating for water. Okay, using the formula we will be seeing how much energy is absorbed by water. Okay, for that we will be using our formula Q is equal to mc delta T. M is there about mass of water, that is 500 grams. Then you have C given 4.18, and for temperature difference you will minus 68 by 25. Okay, now remember, although the unit is Kelvin for temperature, but the difference is always same. Okay, if you convert these two in Kelvin and then you subtract these two, you will get the same answer. Okay, so either you do the difference in Celsius or Kelvin, it doesn't matter. Now if we calculate the Q value, it gives us, I think, 8 9. Yeah, so this is the energy that was absorbed, okay, by water, and this is the energy that was 30% of the energy was released. Okay, this is the same energy. Okay, but we need total energy. Okay, this is the 30% energy. I will write it here. This is only 30% of total energy, because from total energy 30% was only released, which was absorbed by water. So how do we calculate the 100% of energy? We can use a ratio method. Okay, I usually perform this ratio method. What is the ratio method? Like, the thing we need to find out, we keep it on this side, that is energy, and the another thing that is the given, that is percentage. Okay, so if 30% of energy is what, 89870 joules, then 100% of energy will be x. Okay, and now you can do what, cross multiply them. 30x 89870 into 100, and move the 30 on the divide side. Okay, then you will get the total energy. This is our total energy. Okay, but finally what the question asked about the energy, total energy released per gram of methane, per gram, and how much gram you took, 2.5 gram of methane. So just we're going to do what, divided by 2.5 per gram. 2.5, and now you will get the answer that will be around, I think, 119, around something 8 to 7. That we can do like it 120 kilojoules. Okay, to be more specific. So that was the question. Okay, that is how we do the questions. Okay, now one thing more. For example, we will be using another formula as well for this. Okay, that will be enthalpy delta H equal to, I will write the formula 2. For this we will be seeing the questions in paper, in our past papers, and you also have to keep remember this formula as well. Delta H is equal to minus M. Okay, you have a minus sign, then you have all the remaining things as it is, M C, and then you have delta D. Okay, this is a another formula that is used to calculate the enthalpy change directly. Okay, then we have hello, yes, Q over yeah, that is another formula. Yeah, I will be teaching that as well now. Okay, now we have discussed this. So yeah, this formula, okay, we can modify this formula. We can just add, first we will find out, energy released and absorbed, and then you will be dividing it by number of moles, that is N. Okay, then you will get the enthalpy. And apart from that, we can do a question, okay, regarding it. Okay, we'll do the question in topical past papers because the questions are very limited of this chapter, so we will be doing that in our past papers. Okay, and apart from that, one thing more is, I think, left, that is, because I'm trying to see that all the subtopics are covered within this class. Okay, yeah, we need to get a basic idea of enthalpy change of atomization as well. Okay, for that we can okay, I'll just write it here. Okay, so enthalpy change of atomization. I'll just write here one more. Okay, some more standard enthalpy changes. Heading is some more enthalpy standard enthalpy changes. In this we have first enthalpy change of atomization. Okay, for enthalpy change of atomization, we can write it as enthalpy change when 1 mole of gases one mole of gases is formed from its elements. Under standard conditions. Okay, so how do we write the equations? For that, we have, for example, H2, okay, and if we convert H2 into in its atoms, okay, so this is like gaseous and this is also gaseous, but what we have done here, we have broken down the molecule into its atoms. Okay, so you just have to, again you have to keep 1 mole here, so now it will be, after balancing we will do half here. Okay, okay, now do tell me, atomization will be endothermic or exothermic based on our previous concepts? Like we are Endothermic. Why? Because we are bond breaking. Okay, we are breaking the bonds. Okay, so I should wait 5 minutes. Yeah, let me do some one thing. Okay. Okay, let's continue. Then we have like for example, this is for the covalent molecule. Okay, so if I write an ionic any metal as well. Okay, so Na solid. Okay, you know na, Na is a metal, so it will always be in a solid form. So it will be converted into Na gaseous, and there will be no mole changes because both are 1 moles. So every time we are doing what, we are changing the molecular or the solid, or as we can say the liquid form, to a gaseous form. Okay. One more thing, the enthalpy changes. For example, if I take the chlorine, chlorine will have the same equation as we can see in hydrogen. Half of chlorine gaseous, and here we have gaseous. So the enthalpy change, the value of enthalpy change of atomization for chlorine will be half the value of their bond energy. Okay, half the value of the CCl bond energy. I'll write it here because we can see what we are doing here. We are doing half of Cl bond energy. Okay, we are doing this. So the atomization value will be half the Cl bond energy. Okay, and this is the case with every diatomic molecule, whether it is oxygen, whether it is fluorine, okay, whether it is nitrogen. Every diatomic molecule will follow the same procedure, okay, will follow the same concept. And finally, the is always endothermic. Okay, two more we have enthalpy change of solution and hydration. Okay, have you studied them? Because you have not studied them. Some teachers do teach them, okay, because they are included in your A2 as well. So you will be studying them in detail in the A2. Then we have standard, okay. Let me see the formation, combustion, neutralization. Okay, because there were some of the syllabus changes. Before it was included in your syllabus, okay, but now I think they have removed it from your syllabus in AS. Okay, so you should use, okay, define the terms by formation. Okay, you should know the reaction definition, you should know the combustion, and you should know the neutralization. Okay, even the atomization is now not included in yours, but I have taught you because some of the questions will be dealing with some, okay, atomizations as well. So yeah, for that, okay, now the chapter is completed. Okay, now we'll move on to the past papers. Okay, I found the question related to calorimeter. Okay, we will doing the questions on, we can do on this page. Okay. Okay, a student carried out. Okay, I found a question related to calorimeter. So, a student carried out an experiment to determine enthalpy change for combustion of methanol. The following results were obtained. Okay, start temperature, final temperature is given, mass before and after burning of alcohol, and mass of the glass plus water, and mass of glass beaker without water. So, how much of the energy produced by the burning went into the water? Okay, you have to calculate that. How we will be doing this question? Okay, so that will be, okay, you have to, okay, the specific heat is not given here. That will be 4.18 for the water. Yeah, yeah, sure. Try it yourself. Okay, one hint I can give to you is that not every data that is given will be used. Okay, will not be used in the question. What is going on? Okay, are you getting the answer? It would be P. Okay, good. So you basically, okay, let me see. QMC and you have, okay, yeah. So we only need to calculate the mass of water, and then we there was no need to do anything with the readings of ethanol. That was okay. Alcohol, that was even. Okay, now we're going to do a next question that will be again related to, because I want you to get every type of case that we can get, okay, in calorimeter questions, MCQs. Okay. Okay, so should I do the solution? Okay. Q is M, then you have added, okay, 2.5. So, okay, good. So that will be minus 60. Okay. Okay, try to do the questions a little bit faster so that we can do as much questions as we can in this class. Okay, now try to solve this question. Okay, these two questions I have given you, you have to solve them. I'm giving you a time limit that within 10 minutes. Okay, try to solve them.